So the very first thing, and I have this highlighted, is to establish your notation. You can't just start naming things and assuming I'm going to know what you mean at all times, right? So we can say for any number d greater than 0. So here what we're saying is I can label each digit in d as di, where d0 is the least significant digit. This is important because you can label it going the other way. So now what I can say is d can be representative as the sum from I equals 0. Given a number d greater than 0 has n digits. So for any number d greater than 0, which has n digits, n greater than or equal to 1 digits, now we can say the summation goes like this, which is just what we established earlier. So in other words, all we need to make sure we're saying is for any number that we're given that's greater than 0, that happens to have at least 1 digit, which we're going to call n, we can write it down like this in terms of the digits, and we can say that each digit in d is labeled as di, where d0 is the least significant digit. We can also say that the sum of the digits, therefore, so now we can start our proof. We've established some notation. So I want to show is important because now what we're saying is for everything we're trying to show. So this is when we look back at the problem. We want to show for all integers d greater than 0. We know we're doing induction on the number of digits, so it's not enough to just talk about d. Now we're going to say which have n greater than or equal to 1 digits. We write down what we want to show. We say I want to show that d mod 9 equals the sum of the digits, right? So great. I actually forgot to say something here, so I'm going to inject it now. But basically, the other thing we need to remember is we are saying that digit I corresponds to a digit in D. So if I had a number P by any chance or something like that, PI would refer to the digits in P. That's important. This is just on the side. But basically, so digit D subscript I refers to digits in D. Great. And then our next step in induction is now we want to tell our reader how we're planning on breaking down the problem. How is this problem recursive? By induction on n. So step 3 is our base case. And here's another common mistake is a lot of people forget that we're not just because we're doing induction on n doesn't mean we're doing our proof for just n's. Like we are really proving this for all numbers, for all integers. So it's important that we remind ourselves that. So just because our base case is n equals 1, because we're going to start with the smallest number of digits our number can be, this is actually representative of a number d that has with 1 digit. So if we start our base case, what we can see here is I can come in and I'll be like, okay, well, d is equal to saying 10 to the 0 times digit 0, right? I know that the summation from I equals 0 to 0 of d0 is equal to just saying d0. So therefore, I know d mod 9 equals the sum of the digits mod 9 because both of them are digit 0 mod 9. Basically, all we need to know is they're both the same. All right, so step 4 is our induction step. This is another thing that I think people are misunderstanding. The induction step is basically, so imagine if I'm a magician, all right? And I say, pick a card, pick any card you would like. And so let's suppose you're sitting there and you're like, okay, well, I pick a 4 of spades. So I'm gonna do my magic trick for your specific card that you picked right now. Does that mean my trick wasn't gonna work on all cards? Absolutely not. No, it would work on any card. I'm just going to show it for your specific card, which is representative of any general case. So what's important is in your induction step, you're actually introducing all the variables you're going to be using. You're being given a very specific case that is representative of all cases, but it is a specific case. So any name that I use now is taken. So now what I'm saying is I'm given an n-digit number called d. N has some meaning. So if we come up here, when I was given a number here, n had a meaning. N was a 4-digit number at this point. So like this could be a number that my opponent gives me. So basically, and the other step is to understand that induction is basically this proof by cases thing, where it's kind of like the base case and everything else. So this does not include our base case because we're talking about everything. All right. So then step 5 would be our induction hypothesis. Our induction hypothesis is going to say for everything smaller than what we were given. So the reason I'm giving this number a name d prime is because d represents an n-digit number. So if I'm going to start talking about a k-digit number, where I've assigned k to be a value between 1 and n, not including n, then I have to make sure that I give it a new name, because otherwise it'll be confusing and ambiguous. And now I don't just assume that the property is true. I do assume the property is true, but I don't write it like that. I write down exactly what is true. So I write down, I can assume that d prime mod 9 equals the sum of the digits to k minus 1, because now it's a k-digit number, of d prime. So this is important, remember, because we said that each digit, d sub prime of I, now refers to the digits in d prime. And then, so step 6, I like to think of it as a continuation off of step 4. So step 5 is kind of this like, I wouldn't call it a non sequitur, I don't know what the right word is, but it's like d mod 9. This is what I want to show. I've defined it very strongly in terms of what I was given in step 4. So now step 7 is where we do our actual quote unquote proof. But the first 6 steps are really important because we need to know what the notation we've established is at all times. So if we come down to step 7, our very first step I would say to do is to say, all right, well, we should start with one side of the equation, right? Remember when we worked with our little example here, we were like, okay, well, we have our induction hypothesis, we can break this down and so on, and it'll all come together really nicely. So that's all we're gonna do here. We can say here, okay, so let's start with d mod 9, right? I can rewrite that as saying this is the sum of the digits, and that's just given, because that's through my notation I've established, right? Then step 2 would say, okay, well, what do we do with the 4, right? We wrote it down as 4,000. We wrote down a 4-digit number as a 4-digit number plus a 3-digit number. So let's do that here. We can write this down as saying, okay, well, we can take out that 10 to the IDI term for the n-1 plus, and this is, so what we wrote here now is we have our n-digit number plus an n-1 digit number. Our induction hypothesis says that we know that for this n-1 digit number, it'll be equal to the sum of the digits mod 9. We just don't have the mod 9 here yet. So one thing we know how we can get it there is through the mod sum rule. Now we can say, all right, great. So we have an n-1 digit number. I know by my induction hypothesis that for any n-1 digit number, it's equivalent to saying the sum of the digits themselves. And this is by induction hypothesis. So now another common question I get asked a lot is, well, how is that convincing if I just assume everything else is true? Imagine this. So imagine I was giving my 4-digit number, right? And I get to this point and I'm like, if only I knew this was true for a 3-digit number, I can write it down like this. So what I do is I then say, okay, opponent, give me a 3-digit number, and I'm gonna run my whole proof. And I run my whole proof and I'm like, I need a 2-digit number. So I'm like, okay, opponent, hand me over a 2-digit number. And we run through the proof again. And in my proof, I'm like, I can write a 2-digit number as a 2-digit number plus a 1-digit number. And I'm like, wait, okay, opponent, give me a 1-digit number. And I'm like, wait, my 1-digit number is just my base case. Therefore, if I do my whole proof, I would know this was true for 2-digit numbers and 3-digit numbers. So now knowing that, I'm going to start proving it for 4-digit numbers. So what this is it's kind of like the process you would follow for how you could prove it for all numbers that are smaller than it. But this only works because this problem is recursive, which is why induction only works on recursive problems. All right. So then step 5 would say, all right, so we've gotten these digits down. What did we do last time? We did the mod times rule on this. So let's do that. I think growing exponentially is fake. Things should grow moduli. And then our next step would be to now apply the mod exponentiation rule. That's just, I don't know, this is what I would write as my reason, but you can write whatever you want as long as it's clear that yes, because of this line is true. And then 1 to the anything is just 1, and 1 mod 9 is 1. So this is just times 1s by itself. And so this is by multiplication identity. Any number that's less than 9 mod 9 is always going to be the number itself. So once I take the mod 9 of the digit, I already know it's going to be between 0 and 8. Therefore, if I take the mod 9 again, it's useless. So that's the same thing as just saying the n-1 mod 9. Then what we know is, all right, well, this is the mod sum rule again. So we can and then step 11, I can say here, all right, well, we can now put the number back in here, like I equals 0 to n-1 di, which is great. So now we can come back to our step 8 and be like, QED, we can declare our victory and be like, I showed, which is really powerful. The thing I like to do at the very end is I like to look back and make sure that I've answered my question. And well, the question talks about divides. This is something stronger than it. I find it a little, for my own peace of mind, and I think it's always helpful, is to relate whatever you're doing back to what you're trying to prove. So when I'm like, great, so I proved this thing that's stronger, right? So now what I can say is, so let's call this entire induction proof lemma 5.1. And let's come back here and be like, okay, so given any number d with n greater than or equal to 1 digits, I can say step 1, I know that d, I want to show. So I know just by my lemma already that I know d mod 9 equals the sum of the digits, mod 9. And that's just, then my next step would be, okay, well, I know I need an if only if, so I would just go through, and that's just definition of equality. And step 3, this is a mod divides property. We're not going to prove it here, but basically the whole idea is that if something is divisible by 9, right, it would have no remainder if I divided it by 9. Because this implies there's an integer times 9 that equals d, so it implies 9's a factor. If 9's a factor of d, then this is definitely 0. So I can just say this, but you can do the proof if you want. It's pretty sweet. It's a cute little proof. And yeah, and this is just a mod divides property. And then we would be like, cool, we're done. But basically the most important things to remember is whenever we're given a problem, play around with it for yourself. learn how to do the proof. Then see if maybe you can prove something stronger. If you find you're dealing with a property like divides, which is just a really hard property to deal with, then maybe play around with it some more. Make sure you convince yourself there's a roadmap on how you're going to get there. And once you figure that out, make sure you always establish your notation. And then if you're going to prove using induction, make sure you understand what each step means. So you start up by saying, I want to show for everything. I'm going to do it by induction on n. Whatever you're doing induction on, how are you breaking down the problem? Remember, your base case has to represent all of the things you were given at one specific n. So if we're dealing with all integers, we have to make sure we're dealing with all one-digit integers. Your inductive step is for all things that are bigger than the base case. So this is for all numbers that have more than one digit. Your inductive step is representative of all the numbers. Your inductive step is also a very specific case that you're given. Therefore, all of these names are now taken. D now represents an n-digit number, and n is a specific value that your opponent gave you. Therefore, in your induction hypothesis, you need to make sure you don't reuse those variable names. Step 6 looks like step 1, but it's not step 1, because step 6 is telling what you want to show in terms of the specific notation, specific cases you were given here in step 4. And then step 7 is your proof. That's where you have to make sure at some point you apply the induction hypothesis, because it's recursive in nature, and then you declare your victory once you show what you were trying to show in step 6. Don't just declare victory for the heck of it. And then you declare your victory, and then make sure you're just solving the problem at the very end.